Okay, so here's a very good table of the most common polyatomic ions that you'll see in a chemistry laboratory. As you can see that, as the name implies, it's an ion with more than one atom. It turns out that all of these polyatomic ions have covalent bonds between the atoms, but overall there's either a net increase or excess of electrons, one additional electron for a -1 charge, or a net decrease in the number of electrons as opposed to protons, and you can see that for the ammonium polyatomic ion has one more proton than electrons. Okay, you can see that there's a very common, couple of common suffixes for these names, and most notably the ATE and ITE nomenclature. Here's nitrate polyatomic ion with minus NO3 minus. And here's nitrite with NO2 minus. Okay. Now it turns out that this comes from historical reasons. The ATE polyatomic ions are just the most common. They're the most common found in nature. So they were usually the first to be discovered, and they were given the ATE name. Those that were discovered later were given other different suffixes or prefixes, and we'll talk about that next. But there's some polyatomic ions that you should sort of note to memory because they occur so often in general chemistry and in chemistry laboratories. And those are acetate polyatomic ion, the carbonate polyatomic ion. When you add a hydrogen to any polyatomic ion with a multiple charge, we'll call that hydrogen. And of course that hydrogen carbonate, and that will reduce the charge by 1 because you're essentially adding a hydrogen with another positive charged proton. Okay, the hydroxide ion is the basis of our terminology for bases and basic solutions, so that's very important. Nitrate is an extremely common polyatomic ion, so it's phosphate. And again, you can add hydrogens to phosphate to become hydrogen phosphate, or two hydrogens become dihydrogen phosphate, and that reduces the charge. The ammonium polyatomic ion is one of the very few very common positively charged polyatomic ions. And then over here we have the sulfate polyatomic ion, SO4 2-. Again, these happen very, very frequently, or occur very frequently in the chemistry laboratory, so you should denote these to memory. Okay, so how do we change the suffix or prefix? And that comes from the number of oxygens associated with that polyatomic ion. As we said, the most common polyatomic ion is the ATE ion. Okay, and for each individual element associated with these oxyanions, there's a number of oxygens. For chlorate, it's 3. Nitrate is also 3, but for sulfate, you saw that it was 4 oxygens. If you add a oxygen to the 8 ions, in this case chlorate, you go to 4 oxygens, but you keep the same charge. We are going to add the per prefix. So the chlorate ion becomes a perchlorate ion, ClO4, if an additional electron is added. If you remove an if you remove an oxygen from the 8 ion, we change the suffix to ITE. So going from 3 oxygens to ClO2, 2 oxygens, keeping the same charge, we'll call that the chlorite ion. And if you remove 2 oxygens from the 8 polyatomic ion, you add a hypo prefix and keep the ITE suffix. So the ClO -1 polyatomic ion is the hypochlorite polyatomic ion. Okay, so let's name some compounds with polyatomic ions. And again, we're going to use the same general rules that we use for these just metal and non-metal ionic compounds. Notice that if there are more than one polyatomic ions, and there's actually a mistake here, we need to incorporate, there should be a 2 here. We need to incorporate the parentheses to indicate that that is 2 nitrate polyatomic ions associated with magnesium. If you just wrote MgNO3 and 2, there's 2 nitrates, you might think that there's 32 oxygens, 1 nitrogen and 1 magnesium, and that of course wouldn't make sense. That is not a stable compound. So by indicating the parentheses, you're showing that this 2 is for the whole thing, the nitrate polyatomic ion. Okay, because nitrate and magnesium have invariant charge, meaning they do not change, especially the magnesium. We do not need to use Roman numerals, so we are going to name this magnesium, and then the polyatomic ion name, nitrate. Okay, we know that Mg is +2, and we just learned that NO3, the nitrate polyatomic, is -1, and that is, of course, why it takes 2 nitrates to create a ionic compound. Okay, we just saw that NH4 is ammonium, and so we're just going to use that in our nomenclature. Ammonium, NH4 plus, ammonium chloride. Okay, here's another mistake. This should be Na2 SO4, because we know that Na is +1 and SO4 is 2-, and so of course it takes 2 sodiums to produce a neutral ionic compound. But because sodium is a metal with an invariant charge, always going to be +1, we do not need that Roman numeral, so we can just name this sodium and then name of the polyatomic ion, which is sulfate. Okay, here we have an example of a metal with an invariant charge, iron. Iron can take on many oxidation states, +2 and +3 are very common. So we have to figure out the charge on that iron atom, or excuse me, iron cation, based on the anion charge, just as we did before. We can see that this is the hydroxide, so this is OH-. Okay, and so we know that now that this is going to have a -3 overall charge because there's 3 hydroxides. So we know that to make a neutral ionic compound, that iron must have a charge of +3. So this is going to be iron 3 hydroxide. Okay. Another class of compounds that we are going to have to name are known as hydrates. And these are ionic compounds that, if left in an environment that has water vapor, waters of hydration will attach to the crystalline structure of the ionic compound. And they'll do that through intermolecular forces, which we'll discuss at a later section. Okay, so it depending on the ionic compound and depending on the crystalline structure of the ionic compound, a very specific number of water molecules can attach to that compound. And so one example is cobalt chloride, which we can see has 6 waters of hydration. So what we do is we attach a dot at the end of the ionic formula, and then the number of waters of hydration. And it just so happens that 6 waters will attach to each formula unit of cobalt chloride. Okay, remember that cobalt is a transition metal, so we're going to have to indicate what charge it has. We know that chloride has a -1 charge. There's 2 of them. So that must be cobalt 2+ and a chloride -1 ion. So when we name this, we would name this cobalt 2 chloride, but we also want to indicate how many waters of hydration it has with a prefix based on that number. Okay, we're just going to steal those prefixes that you learned in geometry class, and since there's 6 waters of hydration for cobalt chloride, we are going to name that cobalt 2 chloride hexahydrate. Okay, and this is very important because if you are going to weigh a hydrated compound in a laboratory, when you throw that compound on the balance, it is also carrying those waters of hydration. So those are going to increase the mass of the compound. So when we calculate molar masses in a few sections, we are going to need to incorporate those waters of hydration. Okay, if one water molecule associates with 2 formula units, that breaks down to a ratio of about a half a water per 1 formula unit, and we will use the prefix hemi. So calcium sulfate has 1 water molecule for every 2 calcium sulfates, so we would name that calcium sulfate hemihydrate. Okay. These hydrated compounds can also often take on very different physical properties when they are hydrated or not. Some do, some don't. But when the waters of hydration are attached, we call that the hydrate, the hydrated compound. And you can see cobalt 2 chloride hexahydrate has a very rich reddish color. Those waters of hydrations are not chemical bonds. They're only intermolecular forces, as I said. So we can actually remove them by putting them in a very dry environment or heat them away through evaporation. When we remove the waters of hydration and it's just cobalt 2 chloride, we would call that the anhydrous form of that molecule. Okay. So the next set of compounds that we are going to want to name are molecules. And it turns out that they have different rules because unlike ionic compounds, they don't have a charge, so we can't readily figure out the number of elements per compound just based on charge. Okay, so we have to be very forward or very straightforward in the number of atoms per molecule, and so what we're going to do is going to add a prefix indicating the number of elements in the compound. So how you would name this is you put the prefix of the first element, then the name of the first element, prefix indicating the number of the second element, and then even though they are not ions, we still add a IDE, I think just for historical reasons. It should be said that if the prefix is mono for the first element, it's not used, and you already know that, as we'll see when we go over examples. Okay, our prefixes that we use are going to be the same that we use for the the hydrated compounds. Hexa for 6, and the rest are shown here. Okay, so here are several diatomic molecules, or atoms with, or molecules with just 2 atoms, and that's all we're going to focus on here. And so we're going to need to indicate the number of elements per compound. Again, because we don't want to use mono in the first element, we'll need to take that into account. So this is a molecule that's in the news quite often, and you probably already know the name of that. That is, of course, carbon dioxide. And so you're already using the rules for naming simple molecules. Okay, so carbon is just 1, but because it's first, we're not going to use the prefix mono. There are 2 oxygens, so we're going to use the prefix di, and then of course oxide. Okay, you also know the name of this one, and if you tried it, you probably got it right, carbon monoxide. And so these 2 names indicate how many number of oxygens are in that molecule. Okay, so here's another molecule, CCl4. Again, carbon is just 1, so we're going to go carbon, and there are 4 chlorine atoms, and so the prefix for 4 is tetra, so carbon tetrachloride. Here's SO3, so that's sulfur. Trioxide. And here's an example of a molecule with more than 1 atom coming in first, so we're going to need to incorporate the prefix. So this would be diphosphorus. Penta for 5 oxide. Okay, so the last thing we should say or recap is, why is it P2O5 or not O52? Why is it CCl4 or not CCl4? Why do we always say carbon dioxide and not dioxygen carbide? Okay, so there's a simple rule for that, and we had it up here, but forgot to mention it. And we just we read the periodic table left to right, and sort of that's what sets this up. We are always going to put the element that's furthest left first. Carbon is left of oxygen, that's why it's carbon dioxide, and the furthest down. So P2O5, phosphorus, is further down and further left, and so that's where it originates.